Hello, technicians, and welcome back to the Life Safety Troubleshooter. My name is Gary, and if you're enjoying these videos, please like, share, and subscribe. What I'd like to talk to you about today is basically the communications for fire alarms, how it came into being. I want to go over a little bit of history on that. Fire alarm communications or alarm communications have been around a lot longer than people think. It all started with the wet cell battery. And believe it or not, the wet cell battery, as you can see here, which was nothing more than a glass container with an anode and a cathode, an electrolyte or acid, would produce an electrochemical reaction that would cause DC current and voltage. So once they did that, it brought open different prospects for doing things. So after they created the wet cell battery, the telegraph was invented in 1841. Now the telegraph used the wire, an electromagnet, and Morse code that was invented by Samuel Morse to pass signals between different places, different cities, towns. And it started to become a considerably extensive network, was used during the Civil War. But nothing really came of that as far as alarms until 1848. Now, in 1848, what was invented was the electromechanical bell. So now you had a means using these wet cell batteries to cause an audible device, i.e. a bell, to sound in a monitoring station or central office that was being signaled from a subscriber premise. Now, the drawback toward this, of course, is it was an open circuit configuration. So if you cut the phone lines, they were just out of luck. But it did allow for some type of moderate alarms. Now, the problem was, of course, that you had to have a separate wire to each subscriber, and it was all separate circuits to each subscriber. So that part of it was changed when Chauncey McCulla in 1880 invented the McCulla circuit. Now, by chance, that same time, about 5 years earlier, ADT started business. About the same time as Chauncey McCulla, Grinnell started business. So there have been alarm companies all the way back to the 1880s. So the way the McCulla circuit works is basically you would take a single line to a central office, which would be, back in the day, it was an alarm company, not the phone company. It was the alarm company, because believe it or not, phone companies back in the early days actually leased lines from the alarm companies, because the alarm companies are who ran all those cables. And then as telephones became more predominant, that's when they bought out all the wiring and they did their own wiring, and then the alarm companies turned around and had to lease lines from them. But what happened here is you would come into a central office, and in that central office, they would series these lines together, and they would take 2 lines to each subscriber. Now, the way a McCulla circuit works is it prints not only an open circuit, but a ground circuit. So if a line would get cut, you'd still get ground circuits coming in. So how they did that was pretty cool. Basically, and here's a picture of a McCulla wheel and McCulla contacts. And what they would do is they'd wire this up, and you see the top contacts would be the closed circuit, and the bottom contacts, and you notice there was a little bit of screw adjustment there. And you'll notice that there are 2 blades that contact the teeth of the McCulla wheel. Now, you'd program this McCulla wheel by just merely cutting off teeth until you got, in this picture, 217, whatever number you decided to have. So as this McCulla wheel went around, it would open and close the circuit, and then it would ground the circuit. Open, close, ground, open, close, ground. And what that did is it went to a register in the monitoring station. And in this case, you would see 1, 2, space, 1, space, 1, 2, 3, 4, 5, 6, 7. So that's what you would see when I started back in 1978. You would see this on a ticker tape. Now, in the early days, you'd have to sit there and listen to the bell ring. That's why it would send two rounds for an alarm, so they could tell what they were listening to. Then they went to the ticker tape, so it would actually show up on ticker tape, which was basically a tape that was about maybe 3/8 of an inch wide, and it was in a roll. And that's how they did alarms back in the early days before digital alarm communications transmitters. Now, one of the first digital alarm communication transmitter, or DACs, that I ever worked on was a Seskoa. Now, Seskoa was a fire alarm communicator, very early one. It did use 2 phone lines. Another interesting thing is back then, sometimes you needed to have what was called ground start to get a dial tone. So you had a ground start module sometimes that you would tap on the ring and it would bring a dial tone up. But the early format for these DACs was basically 3-1. So 1 was fire, 2 was hold up, 3 was burglary, or whatever you chose for it to be, because it would send 1, 2, and 3. So that was the early days of the format. 3-1 was the start at 10 PPS. And the reason they did that is because they said, well, this was the early days, so they were afraid, well, if the receiver fails or something happens, you could actually listen to the transmission, because it would go dit 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 dit, and you would listen to it, the beeps, and you'd be able to disseminate what customer was sending that code. Now, it did increase from there. That was the start of it. It went to 3-1 extended, where it used hexadecimal. Then it went to 20 PPS. Then it went to 4-2 format, 4-digit account number, 2-digit zone. Then it went to 40 PPS with some check. So now, and we still use 4-2 format with some check, by the way, at 40 PPS. I'm sure any one of you have some older fire panels out there with older communications. And we all know customers, they don't want to spend money unless they have to. Their motto is, it still works. Well, my answer to that was always, hey, let me go out to your car and take 2 lug nuts off of each one of your wheels. That'll work. Sometimes it would change their mind, and sometimes it wouldn't. So, anyway, we know we have to deal with that, so we still have some of these old formats out there. Now, in 1963, approximately, the phone company developed DTMF. Now, DTMF, which is dual tone multi-frequency, that came in around 1963. So what that was, as you can see by what I have up on my screen, 1, 2, 3 to 9 to 0 to star or asterisk pound. Basically, it would allow it to send all those different signals very quickly because it was using touch tones. Now, some of the early ones were on standard phone lines or POTS lines, plain old telephone service. And remember, back in the day, Ma Bell, all these phone lines were copper. So there was really no such thing as latency because it was all copper. And of course, electricity goes at about as close to the speed of light as you can get. So there wasn't any big deal. Communications back there then was pretty stable. So contact ID, in order to understand, back then with no latency, it worked fine. So what happened is that when they invented this, they didn't think about latency. So it was all dependent on timing. So here's contact ID. This is what it does. Now, you notice it's going to get a dial tone. It's going to dial out the phone number. And then it's going to wait a second after it finds out that something's picked up the line. And then it's going to send a 1400 cycle followed by a 100 millisecond space followed by a 2300 cycle tone of 100 milliseconds. And what that's going to do is that's called a handshake. Now, if the communicator hears that handshake, it has to respond within 250 to 300 milliseconds. If it doesn't, then the receiver will send other handshakes for other formats. Now, provided it's contact ID and provided it hears it on time, which back in the day when it was POTS and copper, not a big deal, it will transmit its format, sending touch tones with 50 millisecond breaks and sending what's called a checksum digit, saying, hey, here's one round, here's the checksum that tells you that that one round is correct. And then if the receiver understood that, it would give what's called a kiss-off. So now that was a 1400 cycle signal. So what I want to do here now is I'm going to go ahead and let you listen to what this does and what a normal signal should sound like. And here's this. Now, what you just heard was it calling up, getting the handshake. Now, you hear a little bit of echo in there because this is from a conventional today phone line, okay? So you're going to hear a little bit of weird things in there, but essentially, that's the way contact ID works. Handshake, transmission, kiss off. If it's got another round to send, sends another round. Here's another kiss off. As long as that communicator's done, hangs up. That's what you just heard. Now, moving forward to today, the problems we see are the fact that phone lines are no longer copper. It's no longer the speed of light communication. Phone lines are computer to computer. There is latency. I have a setup on one of my machines in my home where I have a VoIP line that I'm able to control from my computer. And I have Wireshark. So I can literally call up a receiver and see the path by doing a trace route once I find out what the destination IP is. And you would be amazed at how much latency there is if you don't have a good phone line. Most of the failures you're going to have with contact ID is because the phone line is of insufficient quality to support the format, okay? So if you look at an FPA 72, it's going to tell you that you need to use an MFVN phone line. That's Managed Facility Voice Network. And it says it specifically in NFPA 72/2019 that it needs to be MFVN. Now, the reason for that is conventional phone lines used to be able to have a 24-hour backup. That's because it was batteries and copper and not a big deal. My monitoring station I worked for early in my career had this whole room that was just a huge closet full of batteries because the McCulla circuit was basically about 90 to 110 volts DC in order to get out there through the resistance of the phone lines. So nowadays it's computers. So now you've got latency. Now, as you can see from this, contact ID has never changed. Not since it was invented back around in the 1980s. So this is the way it works. And the reason it fails is because of latency, because it's computer to computer. An MFVN phone line is supposed to keep that from happening because it's supposed to be using a much better quality of communications, more bandwidth. That's why the phone companies hate it, because it uses up bandwidth, and bandwidth is money. It also, and this is essentially what is important about MFVN, is the fact that an MFVN phone line has to have an 8-hour sustainability on a power failure at the premise. At the central office or the originating point, it has to be 24 hours. Plus, it's got to have all kinds of different things. So if you get a chance to look it up in NFPA 72, 2019, you'll see where it tells you got to have tornado backups and this backup, and it's got to last for 24 hours. But the important thing is the premise has to be 8 hours. And this is not just if a breaker pops. This is if the whole building goes dark, if the whole block goes dark, if the entire city goes dark. This phone line still has to work for 8 hours. That's why an MFVN phone line is so freaking expensive. I've had customers tell me that they're paying upwards of $600 for each line rated like that. So the thing is, when you're seeing problems with contact ID, and some of the problems you'll see is like when it sends its 24 or 6-hour test, depending on when it was installed. Because remember, in NFPA 72/2013, it went from 24-hour test requirement periodicity to 6-hour test periodicity. And of course, the reason for that is VoIP phone lines, computer to computer. So they changed it to a 6-hour test because they basically made the requirement that the premise had to survive for 8 hours. This is why prior to 2013, it was 24 hours, because the phone company would be able to keep that line running, total power failure, for 24 hours. No longer feasible. So, the best way to get around this and to get the customers to get the proper communications path for that recurring revenue that we all look for in order to keep us going is basically ask the customer, hey, you need to get from your vendor in writing that this phone line is certified as MFVN. And if they can't get it in writing from their phone company, or if the phone company says, sure, it's not, but we can give you that, but it's going to cost you $600 a month for each line, because these phone companies do not want to sell you that line because they don't want to use all that copper and all that bandwidth, because bandwidth is expensive. Now, the way we have changed this is we now provide the path again. In the old days, we provided the path because we had the copper lines on the poles and everything else until the phone company finally got big enough to take all that away, and we had to lease lines from them. So now we can provide that path, and of course we still have to lease that path or pay a service for that path by using digital communicators, cellular communicators. So my company uses a lot of different cell units. One of the most popular is Starlink. There's Telguard. There's Bosch. CLSS, which is the newer type of communications, uses cellular devices in IP. And that's the route that you need to go in order to get good transmission from these customers. If you don't, you're doing yourself and the customer a disservice, because you'll get these comm fails, you'll get late signals. Hey, my alarm went off. I had the fire marshal here. And we set off the alarm, and it took 2 minutes before they called the police department or the fire department. Well, some of that is because of the bad phone lines, and it can't get a signal through because basically the phone line is of insufficient quality to accomplish what it needs to do. So what you need to do is sell the cellular. If you have radio, mesh radio, you can go that route. And also remember, just because you're using a cellular, not all cellular is the same. Remember that phone lines used to be 52 volts, and most cellular units, or even VoIPs or some of these others, use less voltage. On-hook voltage with some is only 30 volts. The lower the voltage, the less it's going to do. It's got to do with volume or amplitude. So one of the units that is good about compensating for this is Telguard, because you can set those up to 40 volts. Now, Bosch is pretty good too, that you can set those. I understand there's some kind of a trick you can do with a Starlink in order to increase that a little bit. But you should all have a banjo, and I'm not talking about that type of banjo. A banjo is a device that you plug in an RJ31X, and then you can clip your butt set onto it, and you can actually hear how it's communicating with whatever path it's using, whether it be cellular or conventional phone lines. And I don't call them POTS anymore. I call them conventional phone lines, because there's no such thing as POTS anymore as far as I'm concerned, because there's no such thing as copper lines coming into buildings anymore that are dedicated to the phone line. So you need to have that so you can listen to it, because not all DACs, digital alarm communication transmitters, play nice with every cell. Sometimes they just don't want to work right. And so you need to be able to troubleshoot that. And in order to troubleshoot that, you will eventually get an ear for it. And you'll hear when it's malfunctioning, when it calls in to the cell unit or the other one, because in these cell units, it's basically a mini receiver. So you'll hear the DAC talk to this cell unit, you'll hear the handshake, and you'll hear it go and transmit, and then you'll hear a kiss off. If you don't hear that, like I let you listen to that, then there's something wrong. If it does the handshake and it doesn't start transmitting, or you hear the handshake and there's a pause and it doesn't transmit, or you hear the handshake and it transmits, but it doesn't stop transmitting when it gets the kiss off, and it just keeps on going and going, you have a problem. Now, you may have to go to a different cellular unit, because, like I said, some communicators don't like to play well with some cellular units. But that's the problems you're going to face out there, that you need to know how to troubleshoot it. And one of the important things about doing that is having that banjo and butt set so you can hear what it's doing. so that you can hear what's wrong. Again, I hope these videos are doing well for you. If you have any questions, please go ahead and I will do my best to answer them. Still a little new about this, so I keep on looking, and if I miss some of them, I apologize. So like, share, and subscribe to this channel if you're liking what I'm producing here. And again, good luck with your troubleshooting. Hope you continue to watch my videos, and thank you.